Hello, this is another video that might be interesting for you, especially for the part or the two chapters, correlation and regression. I'm going to show you using Excel some of the calculations that might help you understand the topic. So this sheet, you will have it already on or LMS. The data that I have a data set here, but before going to the data set, if you remember in one of the slides in the correlation PowerPoints, so we wanted to show you how we calculate the R, which is the correlation coefficient. I'm going to show you here different methods because Excel has an built-in function, but it's very important to understand how the equation of correlation works. So if you go back to the chapters and the PowerPoint, you will find these two equations for correlation coefficient. As you can see here, x minus x bar multiplied by y minus y bar. And you know from now on or before that x bar and y bar are the average. So all what we need to do is to get the deviation from x bar and deviation of each value in y by how far it is from y bar. Then we multiply and then take the summation and then divide by the square root of the summation of individual squared deviation. So as you can see here, all what we need to do is the x minus x bar, because we can, once we get the x and minus x bar, we can get the square and we take the summation and so on. So I'm going to show you how to use this equation to calculate the R. Also, you can see the same R can be calculated using more simplified, a little bit simplified form. So the numerator is the same, but instead of the denominator, it looks like complex, but it can be simplified by using the n-1, which is the number of sample, n minus 1 multiplied by the standard deviation of x, as well as standard deviation of y. But there is also another even more simplified form using the z-score. I'm going to show you the three types here and also compare it to the built-in function in Excel. So the data that we have now is basically this data that you can find them as well in the PowerPoints of the correlation part, chapter 6. Just transpose them to be more vertical instead of horizontal. And then I'm going to calculate the deviation and then multiply them. So I'm going to use here the deviation of x from x bar, the deviation of each value of y from the y bar, and then I multiply them, deviation x multiplied by deviation y, which is the product, like here one. So this is what the book explains, but I'm gonna show you how to calculate it. So as you can see, it's even given. We are given the x bar and y bar, standard deviation for x, standard deviation for y, but I'm gonna calculate that here using the built-in function. So I'm gonna calculate first the average of the x's, like that, and also the standard deviation, stdev.s for sample. Then I take that value here, close the bracket and enter. So you can see we get the same number as given here. So if I drag this to the right to get the same values for y, you can see the average of y is 7 and the average and the standard deviation is 3.39. So if we want to now calculate this x minus x bar here, then I have to take this value minus the 14 and I have to fix it by putting the dollar signs around the column, or you can use shortcut which is in my computer is function F4 or just F4. And if I drag this down, I get 6 minus 14, 10 minus 14, 14 minus 14. So you're going to get this value, which you can see here on the right hand side, the same values here. So I'm going to apply the same thing here for y minus the average, F4 or function F4, down, take it down here, you calculate it. So the same, minus 2, minus 4, 0, 1, 5. Then it's easy now to multiply both of them to get the product. And then I apply it here. Now you can see we need the product, but not only the product, we need also the summation. So the summation of these all values are 72. Then we got the 72 here. 16 minus plus 16 plus 0 plus 5 plus 35, 72. But also if we use the same function here, this one, the second one here, since we have the s and s, and n minus 1 is 5 minus 1, then we can easily get it here like this. 72, I take 72 here, and I divide by n minus 1, which is 4, multiply by standard deviation of x, multiply by standard deviation of y, and then I close the bracket, look enter, push enter, and then I just make it clearer here, so it's easily 0.855, which is actually the same number here. I can calculate the Excel function here using or with Excel. So there is a function called correlation, correl, EL, and now it needs the data of one variable, which is x, comma, the data of y, and close the bracket, and then enter. So I get the same value, and this is the function. So I showed you this one, and we can do this one as well if we want. And it's basically I need to square each value and then take the summation. So if we want, we can do it like that. Just need space here. I'm gonna take here dev x squared. All what I need is to take this value, take the square like that, and I apply it for all values, and I take the summation. So let me take the summation, sum of all this value, 154. I can do the same here for dev y squared. So I take the value here, square it, apply it to all data, and take the summation as it is. So it's very clear here. It's 46. It's actually the same here. You can see there is a built-in function to calculate it instead of doing it like that. But it's no problem to do it step by step, because doing it step by step you will understand more. Don't let X drive you. You should drive Excel, right? So let's take this a little bit around here. So all what I need to do is I took the summation, so I need to multiply them together. So I'm gonna put the multiplication here, multiply by this value, and then this multiplication needs the square root, so I'm gonna get the square root here of this, then I take it like that, then this one. So then I can take the 72 divided by 84, I get the same value. So I showed you multiple ways, and here the formula that I use for each one, so you can always come to it later on to see what did I do. I'm gonna save it just in case. Now I want to show you how to calculate R using the standardized data. In this case we need to calculate the z-score of each value here, so I just put it here. So I want to calculate the z-score of x, and you know z-score equals, basically I take the x minus the average. In this case I'm gonna write the average 14 immediately instead of going back and forth, and divide by standard deviation. Standard deviation is 6.2, and then enter. So I'm gonna drag that to the all 5 points, and I'm gonna do it for y as well. So I'm gonna take the y value from the original data, minus 7, which is, I know it, divided by 3.39, which also we know it. We don't need to calculate it or to refer to the cells to make it easier for us. So I'm gonna take it like that, and all what I need to do here is to multiply both of them, take the product, and then once I do that, so I need to make the summation. So the summation here, I'm gonna write here sum, and the sum equal sum function in Excel, take all 5 products, enter, I get 3.428 and so on. But the equation says you have to divide by n minus 1. So r here, I'm going to write here r equals this divided by n minus 1, which is 4. And again, it's 0.856, which is the same as here, but without approximation, but we can always approximate. So let me take it like that to put it here, and let me make it a little bit like this. So it's more or less similar. There are some definitely round up, round down for each one, so but it's more or less the same number. So now we calculate the r, so I think it's clear now for r. Okay, so I'm gonna stop here, and the next, in the same video, I'm gonna talk about regression. Now I'm talking about regression. It's I want to show the regression in a very well situations. I want to show you first the simple framework, which is the y here. It's the dependent variable. It's satisfaction, and we have multiple independent variables. We are not going to use all of them, but we're going to use one or two to show you the idea, or we use it one by one. We think that our customer will be happy if the product quality will be well, online tracking system if it's good, if the technical support is good, and so on. So you can read them, because this is not the objective to talk comprehensively about this method, but just go ahead here and see that those variables, each one is independent variable, which call it x, and each one is affecting the y, and the y is the dependent variable. So now if I look at the data, this is the data set that we have x6. If you remember here in the slide, it was starting x6, and this is x19. So if I go back here, you'll see this all column here are all my variables in the model or in the framework that I showed you. So 6, 7, 8, and so on until x, until y here. I call out y here because it's y, and each one is x, right? So I can keep this variable like that, and then I will show you something that I related to correlation. I want to see how correlated each variable, if we come here, how each variable is correlated to x19. So I want to calculate the r and the r square as well, as I mentioned in the previous video. So I'm gonna go ahead here, go to my data set, and you might really know that. I'm gonna go to the data tab, and data tab I go to the data analysis tool pack. I hope you know how to install it in your computer. It's add-ins, and I'm gonna use the correlation here option, which is one of the tools. I'm gonna say okay here, and then Excel asks me what data you want to need here to calculate the correlation. Basically, I want to calculate the correlation for all these variables from x6 to x19, but I have to tell Excel, take care, the first row is not data, it's just label, and I want the result to be a new sheet. I call it correlation, or in this case correlations, because it's going to calculate the correlation between each two variables, irrespective how they are. So that means we're going to expect to have a correlation between x6, x7, x6, x8, and so on until x6, x19, and then x7 as well will have another correlation between x7 and x8, x7, x6, x7, x9, and so on. So if I push OK here, you're gonna see what I'm saying here. Sometimes it takes, in your computer might take really very short time. In my case, it takes a little bit longer because I'm using a lot of. Okay, let me make it bigger here. Okay, anyways, it looks like I need to shift one of the point here, but it's not really easy. Anyways, you can see here the correlation between everyone is related to any pair. You can see the diagonal is always 1 because this is the correlation between the variable and itself. So x9 with x9 will be obviously 1. To see much better here, I'm gonna put that like that. I'm gonna color that using condition format. and I go to color scales, and I might really use this color scale. It's not bad. Can use anyone. This not bad, to be honest. Yeah, because the reddish one is a stronger relationship, and the green one is moderate, and the white one is very weak. So let us use this. So you can see here, definitely one is the highest. That's why it takes the red color. But you can see here multiple red, which you can see the correlation is really high. Some of them, they are moderate, so they take some red, but less dark. Green one, it's, yeah, green is here, the negative one, but also might be strong, but it's negative. The very light color, it's the weak color. So you can use whatever the color that you want. Just this is the correlation. So basically, let me write here R. I'm gonna take the same value, nothing really changing here. It's just I want to put some names here, and here I'm gonna call it R square. If you remember from my last one here, I'm gonna take R square from here and take the percentage to make it even interesting, and do like that. Why I took the last one? Because this is the Y variable and each one is X. So basically, this is the correlation between X6 and X19, X6 and X7, X7, sorry, and X19, X8 and X19, and so on. So X19 is the common variable because it's the dependent variable. So this is the dependent variable. The other variables are independent. All of them are independent, right? Okay, so it's not the best here. Let me make it like that. I'll make it better like this. Okay. So, and that's why I took the last one, to be honest. Now, if you look at the highest one, if you look carefully, I know it, it's X9. So X9, to be honest, it looks like the highest. So I'm gonna take X9. It's 36% out of, if it's at the highest R square, which means the highest correlation. For that reason, I'm gonna take X9 here, and I show you now a scatter plot between X9 and X19. So X9 will be the X variable and X19 will be the Y. I'm gonna create a new sheet, put them here, and now we have the two variables. So now I can easily go somewhere here, and I ask Excel to really draw a scatter plot. I'm gonna use this one. So this is the scatter plot of X19, which is the dependent variable, and the horizontal one is the independent variable. Let me make it bigger. And now you can see that I might really need to find a line. And if I take, maybe let me take this line and borrow that, control copy, don't worry about that, control V here. So if I borrow this line, instead of building it by myself, I'm just preparing some stuff here to make it efficient. So I don't know which line I could put here to have the best fit. Remember the discussion. Should I make it like that or like that? I don't know. In the end, it will be very tough for us to do it manually, so we need methods. Excel has a very nice method. If you click on the graph and you find this plus button here, if I click on it and I find trend line here, immediately you see that when I hover over the trend line, a line being immediately drawn between the points, which is basically the best line. Okay, I'm going to take it that. Let me make the color here a little bit lighter. Let me see here. Okay, yeah, I'm gonna make it color. There are marker here, solid. No, the fill here. Let me make them very light. Okay, just to see it better here. And now the line, I can make it now red, and solid and thicker to see it well, and I make it red as well, right? But let me make it straight, something like that. Okay, this is my line. Now I can make it different color. Let me make it green now to differentiate between my line and the line of the Excel, just like that. This I can move it, but the other one I can't move it. Actually, it's built in. So now I have this is the best line, and not only that, the best line is let me take this one. This best line also I can ask Excel, if I go here on the to write the equation and get the R square. So if I do it like this, definitely I will make it bigger a little bit, and you can immediately see that Excel found the regression, and as you know, this 0.595 and the 3.68 are the intercept, and the R square is 3.6 and so on. So if you want to see y is where is the R square is this value, if I go back to the correlation here, you will see here this is the 36.39. If I go back here, you will see it's 36.39. So if you want, we can calculate it here. R, I'm gonna put R here, equals correlation between X and Y, and then I put R square here, R squared, and all what I need here is take this value and square it, so we're gonna get the same number here, 0.3639, 0.3639. So now we have this equation. Remember, this equation has the, if I take text here, insert text very quick, you remember that the y hat, okay, make it bigger a little bit later, y hat equals b naught plus b1 x, right? So, but this is b hat, but I will not be able to do it, but you can, I will put it like this, and then I make it bigger to see this is actually the equation. So now we know the b naught is this one. B naught in this case is the 3.68, and actually is the intercept. So now you see my line, if I put it exactly on the same line here and extend it until y here, you will see is this part became 368. So let me borrow some text here, copy, let me take this as well, control copy. Oh, let me take this as well to make it easy for you. Now go back here, put them here, and let me show you each one. This is the R square, I'm gonna come to it later, but this one is the 368. So B naught is 368, and the slope is basically the 0.595. So here it means the intercept is equal to 368. It means if x equals 0, then the y will be 368. Simple as that. And here it's the slope is 0.595. It means if we increase x by 1 unit, then y will increase by 0.595. So sometimes this equation can be understood very nicely if you try to understand that if this is the total cost, so this is the fixed cost, and this is the operating cost, or current cost. So fixed cost, it will always be equals the cost, even if you don't. So if x is the number of units that we produce, so and each unit will cost us b1, then even if we produce nothing, we're gonna cost b0. So b0 is the fixed cost, and b1 is the cost for each unit produced. So in this case, for each unit we produce, the cost will increase by 0.595. So this is the interpretation of that. So I hope you understand that here. So what else I want to show you? Yeah, there are some interesting thing here, because this is a very interesting thing. Let me see here. Yeah, the R square, I told you the R square is basically here. It says that the R square is 36%. In this case, it means the independent variable was able to explain 36% of the total variation in Y. And the total variation in Y, which is in X here, it's 140 something here. Let me show you how we calculate it. So if you remember, if we get the variance here, variance of Y, let me put it in that way, variance of Y, I'm using var.s, take the data here and enter, and now the total variation in Y, it's basically I take this number, multiply by the degree of freedom, and the degree of freedom is 99 here, because it's I have 100 value here, so I'm gonna write here 99. So 99 is the number of sample minus 1, so I'm gonna get 140.6276. It's the same value here. So this is how we calculate the total variation, and 36% from 140 is attributed to X9 here. This is why it's called 36 here. So another thing I wanted to show you, you remember when we said if we standardize the data, we're gonna get B1 equal R, and we have it here, and B0 equals to 0. So, but again, let me calculate the B1 and B0. Remember B0 and B1? So we need to calculate the standard deviation, remember? Let me calculate here the average. I will call it here Y bar. Also, I will call it the X bar. Let me calculate all of this. And then I calculate the standard deviation for Y and the standard deviation of X. This will help us to calculate the z-score for each one. But also, I want to calculate the B1. Remember B1? Let me take the equation here, because I have them anyways. I have this and I have this. We take them, copy here, put them here, to show you how we're going to calculate both of them. B1, so I need the standard deviation of Y, standard deviation of X. So first let me write here the formula for you, formula text. This is what I did so far, and this is what I'm gonna do in the next couple of things here. So the Y bar, it's easy, average of Y bar here, and here equal the average of X. Now I can calculate the standard dev for Y and equal standard dev for X. So it's easy, right? Now it's easy to calculate B1 now. I'm gonna get this function, which is equals R, we have it here, multiply by standard deviation of X, of Y, sorry, divided by standard deviation of X. We're gonna get the 0.545, which is exactly the same here. See here, 0.595, which is approximated here. B1, B0, now it's easy. If I take the same function here, I take equals the average of Y minus B1 multiplied by the average of X. I get the 368. So everything is clear here, right? So we don't need this anymore. So this is how we calculate both of them. So it's not really a bad idea to do it by yourself, because once you do it by yourself, you understand what's going on. Another point I want to share with you is how to calculate the standardized data. And if you remember, the standardized data tells us something here. Let me see if I have it here. No, I don't have it. Doesn't matter, but probably you remember from the sheet here. I'm going to calculate the z-score for Y. Here, z-score for X and z-score for Y. I'm going to take these two values here as formatting to see the same thing here. All that I'm going to do here is take the X value here minus the average of x, which is here, I will fix it, divided by standard deviation of, I made a mistake here. Actually, this should be minus this value and divided by the standard deviation of x, then enter. We'll do the same here. I'm gonna get here the bracket z-score for each value of y minus the average of y divided by standard deviation of y, and take both of them and actually apply it for each value here. For here, I think. Yeah. So now, if you remember the function to calculate, the value. So come here. I will get you the equation just to make it easy for you to follow. Yeah. Now, if you remember, the equation says if we use this data instead of this data, right? So I'm gonna really, if we make some sort of data analysis here, let me make the regression again here by drawing a curve. And this curve, let me take it here, a little bit here, and let us see. Put it here. I want you to see the difference. So remember, this is for standardized data, so I'm gonna make it bigger here. And now the data is standardized. That's why you see here the z-score for y. But I'm interested in equation. I want you to look at, when I get the equation, what you're gonna get here. Okay, so remember that. Okay, I'm gonna add here a line again, go to the more options, and I'm gonna get both of them. So I'm gonna get here, make it bigger. You will see something interesting, that the R-square is the same even for standardized data, but what happened here, the B0 is 0, because this is actually 0, if you know how Excel make an formatting. E minus 15, it means 10 to the power minus 15, which is 0, and the B1 here is the same as the R. So if you go here, you'll see the same value as R, and this is exactly the same as, let me get the equation, Control copy, go back to Excel, Control V here. This is the same equation here. So that means the z-score, now this y is not the y, it's actually z-score of y, and the x here is the z-score of x, equals this one, right? So that means the R here will be 0.6033. So that's interesting. That means after we standardize the data, the equation will look like this, where B0 will be 0 and B1 will be basically the R. Why? Because the standard error here will be 1 and 1, so it's R, and the average for both of them will be 0 anyways. Then 0 minus 0, then it's 0. So it's very logical here. That's an interesting thing here. What's really interesting, if I get this sheet, I'm gonna call it X9. Let's make it this like that. I don't know if it works, or make it, X9 to X19. I'm gonna do another one here. I'm gonna call it X6 if I want now to change it to X19. All what you need to do is basically you go to the data set here, instead of X9 now take X6 for instance, Control copy, go back to this sheet and replace the first column by the new data and paste. You can see everything change here, every single thing. So you can see R changed, R squared changed, and you will see with the 0.415 here, you will find it here, 0.415 here. The intercept here is 3.675. It's the 0.3675 and 9. And the standardized one will always be the 0.4863, which is the same as here. And again, the intercept is 0, and the R-square is the same. So you can take this sheet and replicate this sheet multiple times, and you change just the first one, the x, by a new variable. You can get it from here, anywhere. You can add now x9, x10, x, and so on and so forth. So I hope it was interesting discussion here, and understand how we calculated the correlation matrix, as well as a regression for original data and regression for standardized data, and as well as how to calculate each component, the slope and the intercept, using the original data, using this function. So I hope you enjoyed it and you learned something. Thank you.